I'm Justas. I will start our presentation, and in the middle, Kliment will introduce his part, and I will finish with some observations in the end. So we participated in CASP15 with three aims. So we modeled protein assemblies. We expected to have much more protein nucleic acid targets. Unfortunately, there were just two and no assessment tables yet. And we also modeled large multi-domain proteins, but our domain definitions were very different from what Andrei said yesterday. So I will be just talking about protein assemblies because the results are the best in this category. So our strategy was to generate a lot of models and select 5 of them and submit them.
Recording in progress.
Sorry. So submit just 5 of them to CASP. So in more detail, we used all the available methods for structural modeling. So standard AlphaFold multimer, we used ColabFold to induce various modifications to standard AlphaFold pipeline. We also use homology modeling. Why not? If a template is possible, and rigid body docking where we thought it is appropriate. And we use our in-house scoring methods based on Voronoi tessellation. Kliment will be talking about this, and these were the methods that were best in Capri scoring. So quite interesting. And in some cases, we tried to find all the available information on the target proteins, for example, in the literature and so on, and do the manual re-ranking based on all this available information. No. Should work now. Okay. So we always started with the standard DeepMind's AlphaFold with full DBs preset, and sometimes we also used reduced DBs preset. And to induce sampling, we use, I will be referring to all of this as AlphaFold in future slides. We used ColabFold, which has the abilities to introduce some custom things. One of them was use different multiple sequence alignments produced from additional sequence databases, including metagenomic sequences. And we also experimented with pairing of MSAs with number of recycles. And we even did the multimer modeling of using AlphaFold PTM, which is not trained for multimer modeling, but it was successful in one case. There will be a poster tomorrow, number 23. All this custom pipeline comes from a real world application on anti-CRISPR proteins. So you might visit for details. Okay, and we used all the available methods to get the information about our target proteins. Some of the methods are developed in our lab. I have a poster on PPI3D. It's a nice web server to find if some templates are available for your multimeric protein. And we are working on making our database accessible for deep learning applications. And we also have a commerce server. It's very similar to HHspread, but with some additional nice features. Okay, so I'm handling to Kliment.
So, hi, I'm Kliment, and first I will talk about docking. We use rigid body docking methods because they're fast. For heterooligomers, we used FTDoc and HEX. For homo-oligomers, asymmetry docking method SUM. And the main thing about our docking strategy was that we tried to dock as exhaustively as possible, and then used our own scoring methods to select 300 best models. We relaxed them with OpenMM to remove some clashes. And then we added those models in the same pool together with generated AlphaFold 2 models. So docking is a win-win situation in this case. Either we generate good models by accident and through, of course, selection methods, or we generate some bad models so that amazing AlphaFold models look very much better in comparison. So about our scoring, this is where things go a little bit sideways. I mean, not in a bad sense, but we do things a little bit in an orthodox way. So we focus strictly on the interface. We derive our interface representation from the Voronoi tessellation of atomic balls, where you basically get an interatom contact surface automatically, but then you can collect all the interchain contacts and restrict them inside the solvent accessible surface and have this nice representation. And more about it in our poster and also in the talk in the QA session. But I would like to emphasize that we used both old VoroMK based interface scoring and also a newly developed method VoroIF-GNN based on graph neural network applications to this representation. We also needed to cluster and compare models. So we used interface contact area difference score also based on this representation. And we combined everything in a pipeline called VoroIF jury. So we have all the models piled together. Docking, AlphaFold, and plane-based models, we cluster them to select representatives. And at this stage, we could, for example, compute for every model a global consensus score, meaning an average interface similarity of a model to all the other models, and select the model with highest consensus score. But we wanted to use quality assessment methods to guide our selection better, the interface focused methods. So we to do this, we, for example, could take just only top one ranked models, pile them together and compute the consensus and select the most representative model. But I mean, those models are not ideal, so we don't really trust top one consensus. So we basically computed top one, top two, top three, top four, and so on. And then we just selected the highest achieved consensus overall, and based on for every model, and based on that we ranked models in the end. So, and I would like to say that this whole idea actually was comes from the EMA jury method that we developed for the CASP Commons COVID experiment. The method was called EMA jury. So I guess thanks to, well, not COVID, obviously, but CASP organizers and the CASP community for doing this. And here is just a little example of how VoroIF jury scores look. So we have top 1, 2, 3, 4, and so on. And we see that some methods, basically our VoroIF GNN and VoroMK energy liked some models from the very beginning. And we trusted the selection basically because the highest achieved consensus was in the top range. But yeah, if we used global consensus score, it would be not a good selection. And I would like to emphasize that we didn't use AlphaFold based quality assessment scores at all. It was probably not the smartest decision, but well, it happened. I think those could be easily integrated in this pipeline. So I will give the mic back to Justas. He has his own mic.
Oh, okay. It's possible to hear. So okay, now I will talk a bit about the results. There were lots of talks today about how AlphaFold is very good for protein multimers. So these are a few targets where no templates were available, even probably for the single chains. And this is even a host pathogen interaction. The thing is how to know if it's a good model. So I think that these predicted aligned error plots could help, because all the models for this target were very good, but for this target, only 1 or 2 models had good predicted aligned error plots. What we noticed in the beginning of CASP season, that AlphaFold fails for large complexes. I don't know the reasons. There should be some reasons, but we decided to model them in parts. So for this large target with 16 subunits, we AlphaFolded the one part, and another part was done by symmetry docking. It's quite interesting, but because it's a ring, and if we could run AlphaFold for, I don't know, 100 more recycles, maybe it would make a ring from this part also. From another target, we had good predictions of the, it's just like a pipe with four tetramers around. So we had these tetramers good, we had the pipe good, and we somehow managed to model with AlphaFold the connection between the pipe and the tetramers, and then aligned and then simply refined to get the whole complex. As Guy was talking about the different mutation interpretation case, these targets were also, they were differed one or two residues, but the structure here, it switched from a bit, and for this one, we had good consensus of AlphaFold models. All the models look the same, and for this one, we had a part of models a bit different, and we just manually ranked the first model to be different from another target. So I guess we were kind of lucky to select the right target for manual selection. And there were lots of talks about how AlphaFold works, doesn't work for antibody-antigen interactions, and the news, not the news, but everybody knows that docking doesn't work as well. It works sometimes. We don't know. We don't know when. So to summarize, AlphaFold works well, but doesn't work with large protein assemblies. We suggest using not only AlphaFold scores, but also other available information from these old school scoring methods like Kliment's Voronki and other methods, and also the template information and so on. And antibody-antigen interactions are hard to predict, and maybe in the future we should focus not only on how to get TM score from 0.95 to 0.97, but to those harder cases where AlphaFold doesn't work. So I have to acknowledge my colleagues. You saw Kliment, Česlovas, and me. We are the Capri and CASP team for last 6 years. Lucas joined from some Nordic country with skis just this year, and we are funded by Research Council of Lithuania, and thank you for your attention.
Thank you very much. So I have a question. So I understand you guys take AlphaFold predictions, template-based docking, and the ab initio docking, put it all in one pool and score, right?
Yes.
So do you have any idea which of the 3 above mentioned methods contribute more?
AlphaFold.
By much or by little?
Well, for some targets, we submitted template-based models as well. We said that it's best of 2020, so this would be our first models 2 years ago. But AlphaFold models were like in terms of interface contact similarity score, twice better. So these were almost experimental structures with AlphaFold, especially when templates were available in the PDB.
I can add maybe that docking worked sometimes, but often when it worked, AlphaFold models were basically the same and they were better.
I think this case probably, or this one. It has good template-based models, AlphaFold models, and docking models. So there are easy cases where everything gets the right structure.
Yeah, it's very interesting to say that you build a very good structure for very large complex H1114. So the example you showed. So I was wondering how, yeah, it's very challenging to do this one because you don't know which parts you only model first, right? How did you choose A4? I think that's crucial. If you get A4 right, you possibly you dock them together. Why did you choose A4?
Okay, we ran first the AlphaFold for the whole. We get some past. So macaroni, long chains not folded. And we decided, so for B2, C2, we had a template available. We found a template in PDB. So it's definitely, we can do B2, C2 model. We did it with AlphaFold. It's this, all these four. And then we inspected manually the results of AlphaFold, these predicted align plots, the consensus of models, and we saw that in all the models, A and B have constant small interface, but it's present always or almost always. So we decided to do A-B interaction. It was in fact A2B2, A2B1. So half of this thing, and A4 we used what we got. So we just got some model for A4, and then just put the things together. It would be nice if AlphaFold would do it by itself, you know.